Thank you. All right, now take it away.
Yeah, thanks for that introduction. And definitely thank you for inviting me here, to talk a little bit about Groq for the next hour. The main purpose really is just to give you transparency into what we're trying to do. I think directionally what Groq is doing, particularly in the compilation approach, is quite different than what you see with, what we've seen in the industry, so to speak. And hopefully this gives you insights as best I can into how we're actually doing that. So today, I'll be talking a little bit about the company and products itself, a little bit marketing-y, but it is a startup. I'm sure most of you haven't heard of the company, so just it helps give you context in terms of what we're actually trying to do. Then with that, I'll jump into the hardware details, just talk a little bit about the architecture. We're relatively transparent in terms of the actual architectural details. We've published at ISCA and other conferences, and have been quite open in terms of how our architecture is quite different than the other vendors. So hopefully that'll give you some context into how we actually map these higher level workloads onto our chip. And then finally, the software approach that we're actually taking, and really contrasting, like I said, to what's been done in the industry. So, a bit about the company. We are a machine learning acceleration startup. So ultimately our product is the development of a chip to accelerate machine learning workloads. Company was founded in 2016 by Jonathan Ross, who was one of the creators of the, essentially one of the first accelerators in this space. So that was being the Google's tensor processing unit, which is pretty pervasive now. So it's almost as though Jonathan was kind of incepted this entire industry, which is pretty neat. Currently, the company is about 200 employees, give or take, headquartered in Mountain View, and we do have an engineering office up north in Toronto, Ontario. We're pretty distributed, I should point out. So we do have a remote first culture. So we essentially have employees spread across the US and Canada, and actually in Europe now. So, we're pretty well capitalized. The point of showing this is not really necessarily to impress this audience, but more just to show that, we do have a fair backing and a belief that we are onto something quite different. And we have the commitment by our investors to really make sure that we can fulfill our long-term roadmap. So we're already working on our second generation and third generation products. And with this money, essentially, we can commit to that and promise delivery of those in the next coming years. So in terms of products, we're shipping something already today. So we have delivered our V1 product. I think the interesting thing about this, and you'll see this when you actually take a look at the architecture, is we were actually able to power this on basically the day that it was received into the lab. And additionally, we essentially went from early silicon to production immediately without a successive tape out that was required. Just to put that in context, so, I've spent most of my career in larger companies, larger semiconductor companies, and, the reality is this is very rare. You generally never have a chip that works straight from the early silicon phase and being able to deploy that into production. So I think it's a real testament to the architecture, and you'll see it's rather simplistic in terms of the overall structure. And obviously the execution of the team is a very small team, and to see them actually execute on this flawlessly is extremely impressive. So taking a look at the overall architecture, one of the things that really jumps out is just the simplicity of it. So here's really just contrasting the architecture against something that you'd see more traditionally in the industry, delivered by NVIDIA or even Intel if you took a look at their die. So the complexity of what most chips have is actually, quite stunning. And it really comes down to a lot of the legacy and inertia that's happened within those designs and architectures. They're obviously making a lot of money, these companies. So, throwing away features or making very disruptive changes to what they've done is, quite costly. And the simplest thing is often to stamp on more IP, or expanding their existing IP as opposed to starting from scratch. Whereas if you take a look at our architecture, this is really something that we stepped back and took kind of a fresh view on. So I think the way Jonathan and Dennis took a look at this, when they were designing this, is really, given the machine learning work space, what would I actually design from that, as opposed to, these are the IP blocks that are available to me. This is how the industry has done it. What are the incremental optimizations that I can do? So it's kind of flipping the problem on its head. And like I said, really starting from scratch. And if you take a look at the architecture, there's really a few key components. There's not much to it. So on both sides of the chip, there's a matrix engine. We call it the MXM, matrix execution module. And that kind of is a highly optimized functional unit targeted for matrix math. Not surprising. In the middle of the chip, there's a vector unit. Kind of think of it as a very wide SIMD based ALU. And it can perform a lot of the sort of generic functions or nonlinear functions that are required in today's machine learning workloads. And then, between those units, there's a ton of on-die memory. And with that memory, you have extremely high internal memory bandwidth. Kind of think of as data can be really streamed in and out of that memory in a very low latency and efficient way. So where we, achieve over 80 terabytes of streaming bandwidth. In terms of raw operations, there's almost a petaop of flops or ops on this chip into 8. And additionally, one interesting characteristic about this chip is you have direct IO in and out of it. So, we have these what we call C2C connections, and you can literally just stamp these chips out like Lego blocks. So you can really scale out the compute capacity of a node by just stitching these things up together. This is just a real primer. I'm sure most of the audience really understand deep learning by now, but at the end of the day, deep learning consists of a graph. Within each node of the graph, it's doing some sort of operation to really, signify some sort of unique feature within your input data set, so to speak. How it does that is often by just performing multiply accumulates. At the end of the day, the vast majority operations within a deep learning neural net is dot products. So naturally, if you take a look at a lot of these architectures that are honed in or optimized for this space, you'll see that they try to optimize the ability to do multiply accumulates extremely well. And Groq is no exception. You take a look at a typical neural network, easily more than 90% of the operations are simple multiply accumulates. So let's go a bit deeper into the architecture. So I think one of the ways that Groq usually explains how our architectures differ is really starting from something that is quite familiar to most folks. So here I'm basically showing a typical multi-core mesh. So within each block in the mesh, there's usually some sort of highly optimized PE. This is often going to be some sort of RISC-based processor, very generic. And if you take a look at a lot of these AI accelerators out there, they basically tune that little PE to be, like I said, very efficient and perform well with respect to multiplying accumulates. So they may widen a vector lane. They may actually add dedicated logic to do some sort of small tensor operation really well. But at the end of the day, the core architecture is going to be some sort of, RISC-based processor sitting there. So there'll be instruction fetch, and then that little core will be replicated across the chip. And then how you communicate across those chips is often there'll be some sophisticated network on chip on the device to allow coordination and communication between those cores. and synchronization. And so it's pretty sophisticated how they actually do that. It works quite well in a lot of cases. I mean, you know, Intel with its Xeon processor family, you know, most inference workloads are still just run on an Intel multi-core processor. So contrast that to what Groq is delivering. So I think the biggest divergence is you can kind of think of us as more of a spatial architecture. So at any given point in space, we will specialize the operation. So what are the knock-on effects of that? So given that any point in space, you're actually literally just doing one thing, but one thing really well, a lot of that control logic and that instruction fetch control plane basically disappears. So you can claw back that logic. Instead of using it to really control the machine, you can use it to sort of stamp up more arithmetic units to do the actual work that is required in these workloads. So here, basically, if you take a look at our architecture, we're basically specializing, kind of cutting up the chip in a bunch of columns or functional slices. And then at each slice, there is a functional unit that does a very specific thing. So for example, I talked about the matrix unit. So those are at the two ends of the chip. And they are literally, all they're doing is a matrix multiply of a specific size. And that's it. So it's very simple. And then, you know, neighboring that matrix unit is what we call our SXM or switching execution model. You know, it does some data transformations across specific vectors, but that's all it does. Again, extreme specialization leading to an extremely simple sort of instruction decode unit that's required for each of these points in space. And then in addition to that, we have our memory unit, and in the middle, there's the functional vector unit. Now, another key divergence is how does data actually move within this chip? And it actually moves on a singular axis, so in one dimension. So again, that significantly simplifies the amount of control logic required. So you can really throw away that network on chip, which is often very expensive. You know, oftentimes most of the area on your device is really just routing wires. So just, you know, the amount of energy and silicon area that's actually dedicated to just moving data is enormous on today's, you know, incumbent architectures. It's actually quite astonishing. Most of the energy is actually in a typical architecture has nothing to do with the actual operations that are being applied within a HPC or machine learning workload. The vast majority is probably just moving data around through multiple levels of caches into register files, and then finally into the ALUs that actually do the useful work. So we throw that all away by our simplistic routing and simplistic data movement. So you can kind of think of us really unrolling, you know, this complicated instruction fetch decode pipeline in space, and then dedicating each point in space to do that really well. So diving a little bit deeper into how data is actually moved on this chip and how, you know, the functional units interact with each other. It really comes down to this notion of streaming registers. So in a typical architecture, what you'll have are register files. So you read from this sort of linear array of registers, pull that into your ALU, get a result, and then write it back into these sort of linear array of registers. What we're doing is quite different, where again, your functional units are somewhat you know, static in nature. It's almost kind of think of it as an assembly line of functional units where data is moving down this assembly line. So there's no explicit instruction to actually fetch data into a functional unit. In contrast, data is actually just moving down this a set of streaming registers. And if they get, you know, if they hit the inputs of a given functional unit, the functional unit will do a transform to it and then spit out the result to a neighboring stream register. So in some sense, the functional unit itself is, you know, quite quite simplistic in terms of control flow. Like it's literally just reading its inputs every cycle and then spitting out a result. So again, there's no need for any complicated instruction decode or fetch unit. And we sort of can regain back that area and use it for more useful operations that are required for our workload. So if you take a look at this, like ultimately the chip is actually broken into 32 different streams. So you can have, effectively, 32 streams of different vectors flowing left to right, and then another 32 going right to left on the chip. And that really leads to this sort of high bandwidth communication and the ability to process a huge amount of data every single cycle on this device. So, one of the knock-on effects of this type of architecture is, it's extremely deterministic. So, this might be a weird thing to focus on because naturally, even existing architectures are deterministic. So usually when we think of determinism is you have a set of inputs and you have a program, given a set of inputs and a program, you will get the exact same output. So I think that's generally the contract that most devices provide to end users. We take that step, further in the sense that we actually are determinist to the actual execution of the program itself, to the exact cycle. So given a program, it will actually execute to the exact cycle every single time that you run it. And it comes down back to the point that there is really no control flow within this device. Data gets loaded from memory, with a read. And then once it's on that stream register pipeline, it's just moving. There's nothing catching it. So literally, if your functional unit is not scheduled or ready to actually process that data, like the data literally falls off the chip. You lose it. So from that perspective, everything happens in a very well-known and predictable manner. And it actually simplifies things from a, it actually simplifies things significantly from a compilation point of view as well. Because you don't have to deal with opaqueness in the hardware and everything is 100% visible to you from a software perspective, you really control the exact cycle when things execute, when things load, and when results actually occur. Yeah, so now that you have hopefully a good intuitive sense of how the hardware is structured, hopefully talking about the software will make a lot more sense here. So basically, again, one of the things that we like to do is really contrast how we're approaching the compilation flow for HPC versus typical vendors. So here's standard picture that you'll see with a lot of the vendors in terms of how their HPC compilation flow works. And this is something that's been quite pervasive in the industry, and it is very powerful. So what you'll find is, there'll be some sort of higher level compiler that ingests a deep learning model. With Google, they have their XLA compiler and it does a lot of these sophisticated operations at a higher level. It'll do node fusion, things like that, and which is very powerful and adds a lot of efficiency to the network. However, once you go to the back end, there's often this notion of mapping those higher level operators to essentially library calls. So, here's a picture of an NVIDIA stack. So they have things like cuDNN, their BLAST library. And effectively what the compiler ends up doing is it takes that high level graph, then breaks it up into these sort of standard library calls or kernels. And that library itself is actually written oftentimes manually. So you're effectively just bypassing the compiler at that point. You're really not trusting the compiler to do anything sophisticated, particularly in the back end. So things like scheduling, at an instruction level, that's all handled by a person. So yes, there's sophisticated ways to write these kernels such that they're templated and a bit more generic. So you're not literally writing a kernel for every instantiation, but at the end of the day, this is very manual. And NVIDIA has done a very good job at implementing this to the point that it's actually quite powerful in terms of their kernel library. They have thousands of engineers. Intel has thousands of engineers working on this as well with their MKL library, math kernel library, and they have a deep learning extension for that as well. And it's, at the end of the day, oftentimes it's necessary to do this at a manual level because a lot of the information isn't known at compile time. And because you do have that sort of complicated sort of synchronization problem and sort of vectorization problem across multiple cores, at the end of the day, a lot of times the best that you can do is doing this by hand. And there's evidence of this time and time again, where a human programmer consistently can outperform a compiler, even today, which is a little bit astonishing since we've been working on compilers for multiple decades, but still seem to be unable to figure out how to do this in an automated fashion. And what you're seeing in the industry, particularly for a lot of these startups, is they're actually following suit with this. And it makes a lot of sense, I think, because if you take a look at a lot of these multi-core architectures, you have to do this. This is really the only path forward. So, I mean, this kind of lends to this quote that I was thinking of prior by Grace Hopper. And, she said that the most dangerous phrase in language is "we've always done it this way." So, this is kind of the culture and philosophy at Groq, really taking a step back and understand what is the actual problem that you're trying to solve from first principles, and then tackling the problem from that perspective rather than incrementally taking a look at what's been done and creating a derivative off of that in the fastest possible way. So if you take a look at our overall compilation flow, obviously I can't be 100% transparent. We are a company, but I'll try to be as transparent as I can. But it's relatively simplistic, but another key thing, it's fully automated. So we don't rely on these sort of lower level libraries in our compilation flow. If you take a look at what we're actually doing is we'll have a higher level model that gets converted into ONNX format that gets ingested into our front end. We'll do some higher level ONNX based optimizations. So things like node fusion, we'll do batch norm fusion, fusing layers to reduce the amount of compute, or element wise, we'll fuse that with some of the convolutions to reduce memory loads and stores. Once that's done, we will do what we call rewrites, which is literally just rewriting the graph into a lower level representation, which is functionally equivalent. So we'll take those higher level operators, break them down, often into vector form, each of those vectors being of the right size that matches into our hardware structures, those functional units. In our case, that's actually 320. So you'll notice, if you actually took a look at our IR after the rewrites, you'll see a lot of operations that are of size 320. It's kind of speckled around throughout the IR. And then once you have that graph, it's relatively static from that point, in the sense that we will not modify the graph structure itself. We're not going to insert more edges, nodes, whatnot, and then we actually just do detailed scheduling on that point. You can kind of think of it as I'm going to traverse my graph, in some sort of order, topological order, what have you, and then literally just start scheduling them on top of the functional units within the architecture, one by one. And that's really it. So we're not having this multi-phase approach where, you're taking these big operators, trying to map them to, it's almost like a tech mapping problem to this well-defined kernel library. And then additionally, having to staff up, thousands of engineers to build up this kernel library, or, trying some interesting techniques to create these templates. So that doesn't really exist. And in terms of results, it's not too bad. So here we're basically showing the utilization of our chip across different matrix sizes. So the dotted red line is, the peak utilization that we think we should be able to achieve in the coming months. The solid red line is actually what we're achieving today out of the software flow. And then the green line is actually what you see in, typical architectures out there in terms of how they're performing in terms of the overall utilization. So, this is a testament to the architecture that we have in some sense, and also the compiler, where we are able to achieve near peak utilization of 100% in some cases. So you can see the dips here, basically because our hardware is sized in roughly 320 element dimensions. So if you don't fit perfectly with 320, like it's not a multiple of 320, you'll see that small dip because you don't perfectly utilize the entire hardware unit at that point. But that's a much smaller divergence than what you'll see in the typical architectures where in some cases you're only using half the chip effectively to perform your workload. And this does lead to inflexibility where you're actually forcing the community to really warp their algorithm or model to fit the hardware versus just doing what's best for the problem at hand. So that's kind of a very simplistic view of how our software and hardware are doing. It's basic primitive, maybe it's a contrived use case, but here's a more top-down view for an entire workload of actually running it through the compilation flow and then running on our hardware. And you can see even for full machine learning workloads, we actually do pretty good. So for transformers, we're able to get extremely good latency. Similarly for LSTMs, in terms of raw performance and peak flops, we do quite well. In some cases, order of magnitude of some of the best known publicly available numbers that we know of that have been published. So, I want to really give you a more sort of tangible taste of how we're actually doing the compilation flow and what we're actually doing under the hood. So, I really wanted to drive that with a simple matrix decomposition example. So that hopefully gives you a sense, at least directionally, of what we're doing under the hood here without going into too much details. So let's say I have a typical matrix operation. So something that's very straightforward. At the end of the day, if you take a look at a lot of these deep learning and HPC workloads, they can be decomposed into basics matrix math. So what we're going to do is actually first decompose those matrices into sizes that are more amenable to what's actually existing on the hardware. So in our case, like I said, a lot of our hardware blocks are sort of multiples of 320. So what we're actually going to do is create a bunch of decompositions or matrices of 320. And then perform essentially a vector matrix operation on those sort of submatrices. So what I'm going to do is break up the first matrix into essentially a bunch of 1 by 320 vectors, and the second matrix into a bunch of 320 by 320 rank 2 matrices. And then what I'll first do is do a vector matrix operation to perform a partial output or partial result. Obviously not the final result there. And then I'll continue that along the first set of columns in the first matrix. And then, end up with sort of a n by 320 submatrix. Again, only partial products. And then I'll move on. So, I'll get the next set of partial product and sum that on top of the previous partial product, and then kind of continue this. You can imagine that I'm just going to do this continually across the entire matrix until I get the entire output matrix calculated. So, how this is actually run on the hardware. What's actually happening is, so let's say I have a zoomed in view of my matrix multiply unit. You can kind of think of it as a plane of 16 by 16 submodules. So here, each red block is, think of it as a 16 by 16 matrix engine. And then we have 20 by 20 of them. What we're going to do, So, as I showed in the previous slide, I'm basically extracting out that 320 by 320 submatrix in the second matrice, and then that 1 by 320 vector out of the first matrix. And then what I'm going to do is actually install that 320 by 320 submatrix into the, let's call it a matrix plane within the hardware. So what this installation phase does is really it takes those weights or those data points and then places them co-resident with a lot of the dot products that exist within that matrix plane. So you don't have to continually load from your on-die memory this 320 by 320 matrix, which could be very expensive and time consuming and drain a lot of energy out of the chip. So then once you do that, then you literally just stream in these vectors from the first matrix. So you can imagine that I'm doing these sort of low latency reads from the on-die memory that's very close to the matrix unit, and then just streaming it into the matmul, the MXM plane here every single cycle. And that's how we achieve the extreme high efficiency, because you can imagine that because the memory is very close to the matrix multiply unit, you can literally get 100% utilization out of this hardware now. And additionally, there's going to be 4 of these. So times that by 4, times it by 900 megahertz and so on, then that's, you can calculate the ops out of that. And it ends up being roughly, I guess with just the matrix engines, roughly 720 teraops in terms of intake performance. So if you take a look at the overall software that we are delivering, so we are delivering our compiler today. So we are shipping today. It's publicly available, the software. We do have a parallel way to program the chip itself. It's what we call Groq API. It's a Pythonic interface that allows you to really control a lot of the low-level details of the hardware. And we found that this is still useful in some cases where you do want to sort of bypass the compiler and just, program each functional unit directly. So we allow users that facility if they need it. And, we have seen some customers actually use it successfully. And then overall, we sit on top of assembler, then runtime, and then obviously, the runtime controls how we actually execute on the chip. So with that, we are shipping a bunch of products today. Hopefully that gives you a good overview of how Groq is actually tackling the compilation problem for our architecture. I think the hope, really what Groq is trying to achieve is really revisiting the way of how we actually take a look at the compilation problem as an industry, and maybe inspire some of folks in this audience and other researchers to really take a look at this compilation problem and kind of flip it on its head and revisit it, particularly for today's high compute demand workloads of HPC and ML. Yeah, and shameless marketing, we are hiring, so feel free to visit our website to look at our postings, see if anything interests you. And that's about it. I'm happy to take your questions now.
Awesome. Thank you so much, Andrew. Let's give Andrew a round of applause. Andrew, just out of curiosity, to satisfy me, were you able to hear the clapping?
Yes, a little bit. I think
just rest assured it was thunderous in the room. So we have a couple of questions from Zoom folks. Shagar, do you want to start off?
Sure. Can you hear me?
Yes.
So thanks for the talk, Andrew. That was pretty interesting. I had a question about the example that you showed, right? So the whole schedule of partitioning it to the matrix into 1 cross 320, is that something the programmer has to write, or is that code a result of a schedule search that happens in your compiler?
Yeah, good question. Yeah, so definitely this is handled by the compiler. We don't expect the programmer to actually do that. And so the way to think of it is what we're actually doing is, so let's say at the Onyx level, I'll actually convert a bunch of things into matmols. And then once I have those big rank 2 tensor operations, those get decomposed in the rewrite phase that I talked about into these smaller, more composable operations that match more seamlessly or align more with the hardware itself. And then once I have that representation as a graph, then I schedule that. And then I can sort of schedule at the 320 by 320 element level is roughly the flow there.
Okay, thanks. Makes sense.
George, you want to go next?
Sure. Thanks very much for the talk. Really interesting. I had a question about the data-dependent computation. So your architecture looks really perfect for dense matrix operations with where you're not kind of skipping out anything based on data values and that kind of thing. But I know that, for example, or my student tells me in the background chat that in Onyx, there is the possibility to support data-dependent computation, and there are conditionals and so on. So is it a subset that you're supporting, or what happens when you encounter data-dependent computation in the compilation flow?
Yeah, good question. So the chip itself is actually, I mean, it's technically Turing complete. I mean, that's kind of a low bar. So we do support control flow. It's not handled the best because it's deterministic. You know, we try to make sure that you know, things run sort of predictably. So you know, some of the ways that we actually handle this. One key way that we've been actually applying this is really pushing off some of the control flow back to the host. So you can imagine that I have these big basic blocks that are deterministic, and those are run on the TSP. And then if there's interesting control flow or data dependent computation, as you mentioned, that gets sort of pushed back to the host for the host to decide what to actually invoke. We do have some examples running in-house of where we actually do this on die as well on the actual chip. And it runs okay, but it's probably not our strength. You know, a lot of the static graphs is probably the key area where we're shining. That being said, so in some instances where the granularity of the basic block is quite large, we still do okay. And we've seen success there as well. But once you go like, you know, you probably don't want to do a sorting algorithm on this chip. It's not probably the best suited, but we can do it, and we have done it.
Excellent, thank you. And one last question, a straightforward one. The Groq API you mentioned, is that described somewhere that we can have access to? Is that public?
Oh yeah, absolutely. There's so we've shipped it to some of the labs in the States, but yeah, and we're talking to a few universities, so I think we're happy to share it.
I think you're coming to us in 3 weeks anyway, so okay, thank you.
Great. I see Steve has a question, but I also wanted to balance it out and get some in-person questions too. Richard, do you have one?
Yeah, should I come up?
Yeah, that'd be great.
So thanks for the awesome talk. I had a quick question about the compilation model. Does it assume that the neural network you're compiling has a particular static layout? And if so, like, how do you go about supporting things like graph neural networks or more dynamic networks that may require live recompilation or something? Thanks.
Yeah, I mean, good question. Yeah, so it kind of rhymes with the previous question there. So, I mean, yeah, so the architecture is highly tuned for a lot of these static graphs, and you can see it from the results. It does a decent job. So I'm, you know, like I said before, for some of these higher level dynamic operators, we'll sort of alleviate that on the host. I mean, but first, you know, some of these other blocks, you can actually do the control flow on the chip, which is required for, you know, reinforcement learning and some of these more sophisticated neural networks where it is actually very data dependent. So the static portion is relatively large. The chip will actually do quite well because, you know, the control overhead of sort of switching or picking which part of the program to execute gets amortized over that big basic block. So it's doable.
Cool. You got a thumbs up in response. Yeah, go for it. Do you want to answer your question? Microphone. That's where we're getting to, Steve. 1 second.
Yeah, hey, nice talk. So I had a question about the utilization slide where you compare against NVIDIA. I noticed that the x-axis goes between like 1,500 to let's say 3,000, something like that. So 2 questions. One is, how do you perform in the range from 1x1 matrices to 1,500 by 1,500? And part 2 is above that range, right? So for current large language models, which scale to thousands of TPUs, right? Like how can you handle, like can Groq handle like 1 trillion parameter transformer models? Thanks.
Yeah, very good question. So for these extremely small problems, yeah, like we will totally underutilize the chip. And we've seen some of those cases with some models that are essentially tiny, like 6x6 matrices sizes. At the end of the day, you have to kind of fit that 320 by 320 block. If it's extremely slow, you're just going to totally underutilize that. I mean, you can do some tricks. So let's say I have a 6x6 matrix, you can kind of stamp out a bunch of them on the diagonal, but you're still going to severely underutilize that piece of hardware. So what you would expect for those smaller matrices, like, and we've seen this, is the utilization will actually drop, particularly for the tiny matrices, like below 50% even. And that's expected. So I think there's nothing surprising there. I mean, the good thing is most problems that are that small, it's fine to really underutilize the hardware because everyone will, quite frankly. So I think it's okay that for those sizes, as long as we still hit the SLA of what the customer needs, we're good. So conversely, for these massive, GPTs that we're seeing and all these like huge transformers, and this is true for CNNs as well. Like once you go to HD images, you have a ton of activations. So the live state is massive, not necessarily the parameters or the weights. So it's kind of the dual problem there. So how do we handle that? So there is, you're absolutely right in seeing that there is no external memory on a singular chip. What we've seen, and we have this support, is you can actually leverage the host memory in some instances. Over PCIe, the latency is not that bad, so it's almost like the x86 processor, pairs with the accelerator and lends its memory space. So that's one way to handle it. So you kind of tile up your problem and just solve either sub portions of that problem on the chip, or in the case of very large transformers, like you can just serially execute each encoder, right? So if go from BERT to BERT large, let's say, you can actually just load sub encoders first, execute that, store the result on chip, or even spill to memory if needed, external memory, and then solve the next 3 encoders and kind of move it that way. That's one way to handle it. Second way, and this is the way that is more interesting to us, is really you can extend the chip itself. Like we have those high bandwidth connections. It's kind of analogous to the GPIO on FPGAs, but you have that direct connectivity directly into the chip through those C2C connections, and you can literally stamp them up like Lego. And then you effectively are increasing your SRAM capacity at that point, where each chip you can store roughly 230 megabytes, and then you just replicate that out to create a larger cluster. Hopefully that.
So yeah, so just a quick follow-up. So for these interconnect, right, your compiler is kind of dependent on determinism for correctness, right? So are your interchip interconnects deterministic, or how do you handle that?
Yeah, very good question. So it's a bound. So you can kind of think of all devices at the end of the day. If you make the bound big enough, it'll be deterministic, right? It's kind of an interesting way of thinking of it. We so happen to be able to have that bound very tight such that it's very predictable. So within the die itself, literally to the exact cycle, you know. As you go through those C to C, I think you're absolutely right. There's going to be a variable range, but it's, you know, there is no flow control per se within that C to C link. And, you know, they're characterized and sized to the point that you actually know to a pretty good predictability. And there's, you know, a very small buffer actually behind the read portion on the link anyways to catch, like, allow for some variability. But it's sort of very tight in how we designed it.
Cool. Steve, you're finally up. Thank you for your patience.
No worries. I'm curious if you can comment a little bit on your use of MLIR and what you like and what you dislike. I assume if you're coming in through Onyx, you're using Onyx MLIR and doing a lot of the tiling at the affine level.
Yes. Yes, you would be correct. I mean, you know, definitely the flexibility, right? You know, we have our own proprietary IR that we're handling. You know, it slowly transforms through the rewrites that I showed. That's been fantastic, you know, and having that is great. You know, obviously all the infrastructure that it provides natively, that's been very useful. I mean, one slight pain point and annoyance is just, you know, the way it stores attributes and things like that is a little bit expensive. And, you know, sometimes you get bogged down in runtime and speed in some instances. There's a way to get around that. You know, you can convert everything into like function parameters and things like that, and that definitely helps. So there's some, I guess, you know, baggage, it feels like, with, you know, maybe unnecessary. I guess maybe in some cases people need it, but it just feels like some of the objects itself are a little bit heavy, more heavy than they need to be. And it'd be interesting if there's a way to make a bit more lightweight, you know, particularly for our backend, because we're doing detailed vector scheduling on pretty big graphs. You know, these can be millions of nodes. Like, you know, speed is very important to us. And even just sometimes traversing the graph, it takes a while.
Cool, thanks.
Yeah.
Well, let me get a last round of questions from anyone in either modality here. If you don't mind, I just had one super basic question I wanted to clarify, which I didn't quite get, like, how much, if any, of this is open source, that is like the compiler stack that is like, or even if it's not open source, I guess I'm curious, like you talked about the low level IR. Is that a thing that other tools can target, or is that a proprietary specification? Does that make sense?
Today, no. Definitely, it's something that we've been chatting with a few labs about, if it's something we could open up. But today, the official stance is no. Front end stuff, we've upstreamed stuff into Onyx MLIR. So a lot of the stuff that's device agnostic, we're happy to share with the community. But generally, once you have some of the device stuff and definitely our dialects in the MLIR, we haven't open sourced that.
Great, cool, thanks. Awesome, thank you so much. One more round of applause for Andrew, please.
Thanks, everyone.
Thank you so much for coming. That was really awesome. We here in person are going to take a break for half an hour-ish to come back at 4:30 for our final session. And I think that fairly shortly there's going to be snacks outside. So again, sorry to the folks online. Please find your own snacks. And if you want, we'll see you in half an hour. Hi, everybody. We are going to wait just a couple of minutes here before getting session 4 started. Zoom folks, how you doing? Doing okay?
Starting to wake up.
All right, awesome. Glad to hear.
Adrian, this is Adel from Illinois. I have a question. How is this session going to go? Because I haven't been able to catch any of the previous sessions.
Oh, no problem. Here is the outline. We have 3 talks, and the way that those will go are that the talk video plays. We have a moment for any quick clarifying questions from all attendees in both modalities. And then we're going to go through all 3 talks that way with very brief clarifying question sections at the end. And then together at the end of the entire session is going to be an actual discussion period where your questions surface. And the way that works is in 2-phase approach where there are small breakout groups for your initial round of questions. And then the best questions that surface from those, you bring them up in sort of in the plenary thing after all that. Okay, I realize that was a lot of explanation, but did it make any sense?
Yes, it does. So yeah, so then because the schedule says it's only 30 minutes for this session. So
yep, somehow this is absolutely my fault. Just to be clear, I like allocated the time to the papers. I missed that some of the sessions needed more time. Anyways, this is going to go a little bit longer than 30 minutes. Sorry about that.
No worries. Yeah, thanks.
All right, I think we're going to get things started here. I need to do some jumping around to share my screen. Oh my God, we've been recording this whole time. Come on now. Sorry, just 1 second.